just before we conclude, and the first paper presented by Sergey on privacy preserving Know Your Customer on Ethereum.
Okay. Yeah, welcome everyone. It's a pleasure to be here, and I'm going to present our recent work with Professor Alex Berikov and Dmitry Kovratovic regarding the privacy preserving KYC on Ethereum. So we are dealing here with the problem of digital identity. How can we deal with decentralized digital identity, and how can we respect users' privacy and at the same time make this technology compliant with the laws? So here's the brief outline. First of all, an introduction, some basic notions that we are going to deal with. Then I will describe our proposed architecture for identity management for decentralized financial services. And then I will conclude and discuss some future work and research questions that will go on this whiteboard. So identity in general just is some data that represents a user in a digital system. And it's used for basically authentication, that is making sure that the user is really who they claim to be. And then the next step, authorization, making sure that the user is eligible for the action that they are trying to perform. And if we reformulate this question in cryptographic terms, essentially we're trying to maintain the correspondence between real-world identities, such as users or companies, and public-private key pairs, where users use their private keys to send messages, to do some actions. And the prevalent model today is centrally managed identity. So when we use like all the popular services, we log in with our password, and we are granted access to the right to do some things, but nothing prevents this, the system, technically nothing prevents them from revoking this access or doing some actions on our behalf. So in the end, we still trust these centralized services. And this, of course, on the one hand, it provides some efficiency, but the drawbacks are that the identity theft, the risk of identity theft is big, and it's just a central point of failure that can be exploited by hackers, for example. And now a very promising direction in the decentralized blockchain research and development are decentralized identity. So the idea is to put users in charge of their own data, make them have the power over their credentials, which services can use which pieces of their personal data, and it actually can be implemented using blockchains, public blockchains such as Ethereum. But two questions that our work is mostly focused on is, first of all, does this new technologies respect users' privacy, and to which extent, which privacy guarantees do they provide, and how does it all correspond to the existing regulations, for example, with GDPR that we discussed yesterday, but just in general regulations regarding Know Your Customer. So just kind of a quick recap, a quick background to remind ourselves what started this whole journey that we are all parts of. Bitcoin as a first decentralized digital currency introduced in 2008, and the main innovation was to combine cryptography and economics to provide security guarantees. But in our system, we are mostly dealing with Ethereum, and we are implementing our solution on top of Ethereum because the main feature that distinguishes Ethereum is a Turing-complete programming environment and the programming languages that make it possible to implement arbitrarily complex logic, with some caveats, of course, but in principle it should be possible to implement anything on Ethereum. If we go a little bit deeper, one of the most popular applications of Ethereum, one of the most popular examples of Ethereum smart contracts are what is called tokens. And you probably heard about tokens in terms of ICOs and these immense valuations that new projects get when they issue their tokens and sell their tokens. Actually, a token is essentially just a smart contract that maintains a list of balances or a mapping of balances. It remembers which user owes how many tokens and let users transfer tokens between themselves. And ERC20 is the name of the most popular standard. It's the de facto standard for implementing tokens on top of Ethereum. And as an example in this presentation, I will use decentralized exchange. So decentralized exchange, it's also promising directions. Multiple projects are pursuing this idea to develop an exchange so that users can swap tokens of one type for tokens for another type, or tokens for Ether and vice versa, without trusting any central intermediary, just doing Ethereum transactions entirely on chain. And if we're trying to implement these decentralized exchanges, then the question arises what kind of privacy guarantees does it provide, and if it can be made compliant with KYC regulation. So yeah, this is basically the three main functions that a token can have. So I can just transfer some tokens, if I have some, to some other address. I can also approve, that is, give some other user the right to spend some amount of my tokens on my behalf. And on the other hand, if I'm granted this right from some other user, using the function transfer from, I can transfer their tokens to some address of my choice. That was kind of a background introduction. Here I'm going to talk about our proposal, our identity management design for financial services. Our main goal was to make this system decentralized so that it could be used, for example, for on-chain exchanges. Make sure that it preserves users' privacy in the sense that, of course, if the law requires, the user discloses some personal information to some entity that does the verification or does the eligibility checks, so to say. But we want to make sure that this personal data is not shared with anyone else. So ideally, only with the parties that are required by the law. And we can also extend our design not only to decentralized exchanges, but also to possibly other types of financial applications. But as an example, I will use a decentralized exchange. So our main cryptographic technique that we suggest would be useful here is called a cryptographic accumulator. So this is a cryptographic object that provides us with the following functionality. It can absorb certain objects, so it can accumulate values, and then it can be used to prove in zero knowledge that certain values were accumulated or were not accumulated. But the most important thing is that it's impossible to extract individual values from the accumulator. But if I want to check if some value was accumulated, then I can query the accumulator and it will give me the answer yes or no. So in that sense, it preserves privacy, and we suggest that we can use this cryptographic technique to implement our privacy-preserving identity management system. So this is how our proposed workflow would look like. First of all, there is this entity called a KYC provider. It may be a governmental agency, or it may be some other company in charge of customer onboarding. It's not so important for our design. So if I want to be checked and to be eligible for trading some exchange, I contact the KYC provider and possibly do some offline interview. I provide some documents like as the law requires, and then my value, some kind of serial number, is being accumulated into the accumulator by the KYC provider, and the accumulator is stored in a smart contract on chain, and the provider issues a special value for me, which is called a witness, which will let me prove in the future for any financial service compatible with the system that I actually have been checked by the KYC provider. So if I have this witness, I can then go to any financial service, and using the witness, I provide an atomic zero-knowledge proof of the following facts. So first of all, I know the private key that corresponds to my address. Actually, I am the one who is doing this transaction. And second of all, I know I have been checked by the KYC provider, and I know the witness that some value was accumulated in the accumulator. So in that scheme, the financial service will not get any of my personal details, but still will be able to check by themselves using the same KYC provider smart contract that actually I am eligible for the transaction. So here's what the interface of the KYC provider could look like. It can, one function can add a user so that the user is able to trade some token. It can remove user from the list of the eligible users for whatever reason, and it can return us a Boolean value whether the user is eligible or not. Of course, the revocation functionality is also available if the KYC provider detects, I don't know, maybe some kind of case of fraud or some other reasons to withdraw my permission. It can update the accumulator so that my witness will no longer work, and I will have to contact the KYC provider again and get a new witness if that's still possible. So I will briefly describe two possible use cases. So the first use case is KYC compliant exchange. So we imagine some some token exchange, some cryptocurrency exchange that wants to implement certain kinds of KYC measures, and they implement the system. They say sign a deal, they sign a contract with the KYC provider. KYC provider deploys the smart contract with the accumulator. The exchange changes their code so that before every transaction happens, the checks are automatically performed whether the user is eligible. And in this scheme, the token itself does not need to be aware of the KYC. So the token just exists as a smart contract on the blockchain, and it, from the point of view of the token, nothing changes. Just some transactions may pass or may not pass depending on what happens in the exchange smart contract. So this is one scenario that we review in the paper. And the second scenario could be a compliant token, or a token with the built-in KYC check. Here, on the other hand, exchange does not need to know anything about KYC. Exchange just works as usual. But inside the token contract itself, before every transfer can happen, there is a call to the KYC provider contract, and eligibility check is performed on chain before every transaction. So this is kind of the other way around, and a possible use case that we envision. So there were some use a couple of years ago about, for example, Bank of England and about the Monetary Authority of Singapore announcing, issuing press releases on that they are thinking about issuing their own cryptocurrency or their own token. And we think that a possible future use case would be that governments will issue their own tokens or their own currencies for the purposes of, say, paying taxes or paying fines or interacting with the government in some ways. And those tokens could be, for example, tradable or exchangeable only by the citizens of this country. So this might be also a use case that we will see in the future. So here are some implementation details. Actually, what's being implemented is just a proof of concept implementation, and this is not yet privacy preserving. We pitched this idea, and we presented this proof of concept implementation at a hackathon called Loops Block Hackathon in Luxembourg, which happened exactly 1 year ago. And we were awarded the first prize. We actually shared the first prize with another team. And yeah, here are the members of our team, excluding myself. So the main technical challenge, the main technical difficulty that arises if we want to fully implement the proposed design is that the accumulator implementation requires a significant amount of computational resources. And in Ethereum, as you might know, every computation must be paid for in terms of gas, and each block has a gas limit. That means that despite the fact that the language itself allows us to implement whatever we want, we are not able to actually execute whatever we want on the real Ethereum network, because the gas limit will soon be, we will soon spend all the available gas. So we were not able, for the moment, to implement all the cryptographic operations required for the accumulator for it to function. And there might be multiple paths forward. So first of all, we might either just hope for or help implement these cryptographic operations inside the main Ethereum client. So the Ethereum clients, such as GETS, support certain cryptographic operations natively. That is, there are some opcodes in the EVM bytecode that just execute, I mean, not in the Ethereum virtual machine, but on the, say, bare metal. And in October last year, there was the Byzantium update, the hard fork of Ethereum, where they introduced, for example, zero-knowledge checks, which let check zero-knowledge transactions on Ethereum. So that shows that it's, in principle, it is possible to add new sophisticated cryptography into Ethereum opcode so that it does not add up towards the block gas limit. So that can be one way to implement that. Another way could be to investigate some kind of off-chain approaches. So the main performance the most performance-intensive operation is updating the accumulator. So we could look into some kind of scheme where we do this operation on-chain and provide some kind of cryptographic proof that the operation was performed correctly. That as well is a possible direction for future work. So this is the main technical challenge, but in principle, it should be possible to implement. Maybe on some say on some private fork of Ethereum, which would support this sophisticated cryptography. So in conclusion, I would like to say that as we studied in this work, Ethereum, on the one hand, Ethereum, as just in general public blockchains, provide us with this amazing way of not only encoding agreements in digital form, but also enforcing agreements in digital form. And cryptography allows us to provide additional security and privacy guarantees, techniques such as zero-knowledge proofs or cryptographic accumulators. But many technical challenges are in the way of fully implementing this idea, and this might be a very promising area of research. How can we merge the inventions of cryptography, this lesser known but very powerful cryptographic algorithms, with existing public blockchains such as Ethereum? So the research question that I want to share with you, which I think is really important, is how can we leverage sophisticated cryptography in public blockchains such as Ethereum to provide stronger security and privacy guarantees for the users of these blockchain systems. So with that, I want to conclude, and here are the links to the website of our group and to my personal website. So I'm ready to take some questions.
There's time for several questions, if you like.
Yes, well, I'm fascinated by this concept of a know your customer provider, a KYC provider that takes a lot of that burden from the other players and does all the privacy stuff. So how do the fail scenarios work? For instance, I want to trade more than 10,000 euro, or I've done something criminal, and there's a lawsuit that asks who I am. How does that work? I mean, know your customer means know your customer in that sense.
So if, for example, if law enforcement wants to get some of my personal details,
yes,
they can just go to the KYC provider with the court order or something, because I provide my personal data in plain text to the KYC provider, and it stores it somewhere in the internal database, but does not reveal it to the whole world and to other financial services. So that's the idea. So we concentrate this data. I mean, we store this data in one place where it must be stored by law, but we don't expand this risk onto other players.
So which cryptographic primitives would you need to be implemented in the Ethereum VM?
So actually, yeah, for the cryptographic details, I can refer you to the paper, but actually we want to be able to calculate the pairing that is required for this accumulator construction. So as far as I understand, we can already check whether the value is accumulated, but in order to add a new value to accumulator, we have to do multiplications, which are not yet available, multiplications in this elliptic curve finite fields.
I have a question regarding the size of the accumulator. Assume that, for example, I've added 10,000 operations.
No, the main benefit is that it doesn't grow in size. It's constant size.
Yeah, so I'm building a protocol Byzantine fault tolerance for eventually persistent databases, and I would need from time to time to send a kind of certificate like this accumulated cryptography to the client to verify that previous operations have been executed. So would it be efficient to send this to the client?
Maybe. I think it depends on many details, but I think you may investigate this approach, and I don't know, probably yes, but I'm not sure. It depends on many details.
The size of the accumulator is in terms of megabytes, or?
I'm not sure actually. I'm not ready to answer this question now.
I will have a look at the paper.
Can you show the last slide again? So,
This one?
okay, sure.
All right. We do have time for one more question if you like. I'm wondering to, maybe if I can also ask you a question. Of course, trust is a big topic in blockchains, and here, obviously the KYC provider needs a certain amount of trust from other entities. But there's multiple entities that may have those trust requirements. We already mentioned like governments, but also possibly the other service providers. Did you think about the element of trust and how it extends and how these requirements would propagate to the KYC providers?
I mean, KYC provider is not, we can think about it as some kind of government legacy as well. It's just, it's not some kind of random entity. We have to trust someone. If I'm required by the law to provide my personal data to someone, I have no choice. I may trust them, I may not trust them, but I have to provide it anyway if I want to do something. But our idea is to minimize this number of parties who I have to trust or whom I made to trust by the law. That's possible.
That's from the user's perspective, but the KYC provider has to also, so there have to be, let's say, some that are allowed to be KYC providers in general. Not everyone can walk up and say, I'm a KYC provider now.
Yes, it's outside the scope of the technical solution itself, but in the real world, I suppose, yes, there will be some kind of licensing, or some, so the government, say, would issue a license to be a KYC provider, and then the KYC provider will do its business. And
all right.
So I'll give a comment on this that supports this. I think in Portugal they started to give digital signatures for people. So this is kind of
like Estonian residency, like along these lines.
There was one more question there.
You mentioned zero knowledge proofs. To my best knowledge, I'm aware that with zero knowledge proofs, you always need some party that you trust to basically set up the whole system that the zero knowledge proofs can work system-wide. Are you aware of any approaches where you don't need this trusted party for zero knowledge proofs?
I think, the exact answer to this question would be, it's better to look up the paper, not even in our paper, but the paper that we link to that describes the exact cryptographic construction. And the limitation that you're talking about is relevant for the Zcash cryptocurrency, which uses use the trusted setup to agree on the set of parameters. But here, still we have a trusted entity. So if we, in this design, we are dealing in a framework where we generally trust, say, the government, or trust the KYC provider, or we have to trust them. So we may as well trust them to do this setup ceremony and choose the parameters.
Maybe the next speaker can come up already, and let's thank the speaker again. And maybe you can put your question on the board.
Okay. I took a copy.
Oh, you took a
I took a copy. Yeah.
Oh, okay.
I took a picture.
So for the last talk of the day, we're going to hear about an evaluation framework for blockchain in the public sector and the example of the German asylum process.